what I'd like to do is to make a presentation to you all on the subject of Adeline and the training algorithm for it, the LMS algorithm. The Adeline neuron and this training algorithm was all developed in 1959 by myself and my first doctoral student, Ted Hoff. I'd like to describe how these devices work, what they're all about, and how the adaptive algorithm works, and tell you a little bit more about LMS algorithm. What I'll show you is two pieces of equipment that we had built. The one here that my hand is on, this was built in 1960. And the second one was built, I believe, in 1963. So these are quite old pieces of equipment. Amazingly, they still work. These are trainable, single adaptive neurons. And they're both trainable with the LMS algorithm. LMS stands for least mean square. So we'll talk about least squares solution, Wiener solution, all sorts of things that have to do with this kind of adaptation. Each of these devices is a single Adeline neuron. We have an array of switches that allows the input of a pattern. The input pattern, the switches are the pixel inputs. So this is 16 by 16. I'm sorry, this is 4 by 4, so the total is 16 input pixels. Each pixel is either switch up +1 input or switch down -1 input. So they're binary inputs. In principle, doesn't have to be binary, it could be analog. Each switch connects to a coefficient, and these are weights that are adjustable by hand. And I will demonstrate the training of this device and show you how you can adjust these coefficients to cause this simple device to learn to classify patterns. The second device does the same as the first device. The inputs are applied with switches as before. Each input is either +1 or -1. You'll be able to see in the array of lights what the input pattern is. It looks like ones and zeros, light lit, light not lit, but actually it's +1, -1. You apply the input patterns and you train it by adjusting the adapt switch, which I'll demonstrate to you. And what you can see is the output response of the neuron for each input pattern applied. Now this Adeline doesn't have mechanical adjustable weights or coefficients or synapses. In this one, the synapses are electrochemical, so it's an electronic control over the weights. The weights are controlled automatically in accord with the LMS algorithm. So I need to explain how the LMS algorithm works and exactly what all this is. We have an input X, which is an input pattern. Each pattern has a set of components. On the two Adelines that I've shown you, the inputs are either +1 or -1, yet in principle, these inputs could be analog. Each input goes to a weight. These are the weights. We form a weighted sum. This is a summation. So Y is the sum of x1 multiplied by w1, x2 multiplied by w2, all the way down to xn multiplied by w sub n. Now there's a special weight called the bias weight. That's w sub 0. Its input is always +1. The inputs here change from input pattern to input pattern, but the input to this weight never changes. The coefficient here determines a bias that you're adding into the sum, and that will give you the possibility of having a bias in the output if you need it. When we're training this thing, we feed in a set of input patterns. For each input pattern, see, we lost a little bit of our X here. For each input pattern, there's a desired response. We tell the neuron what we want the output to be for that input. We compare the desired response with the output response. The difference between the two is an error signal, and the error is used in adapting the weights. Now, the weights are represented by circles with arrows through them. The arrow through the circle indicates that the coefficient, or the weight, is adjustable. So the error has to do with adjusting the weights, and what we'll do is to adjust them to minimize the mean square of the error averaged over all the training patterns. So we have a set of training patterns. Each training pattern is an input X and an associated desired response. So we feed in the set of input patterns, we adjust the weights, and the purpose is to minimize the error, not only for the individual pattern, but over the entire set of patterns. On average, we want to minimize the mean square of the error. So this is a least squares approach. Minimizing mean square error means that you minimize the square of the error, so positive errors and negative errors are treated equally. They're both bad. Errors are bad. So we try to get rid of errors. We'd like to have zero error, if we can get it, over the entire set of training patterns. Now, sometimes we can do that, sometimes we cannot. We can get zero error if all the training patterns happen to be linearly independent, and the number of training patterns is equal to or less than the total number of weights, total number of inputs. Okay. Now, on these two Adalines, the output is indicated by the reading of a meter. You may recall when we looked at the Adalines that you saw a meter, but you'll see plenty of the meter when I demonstrate. So the output is fed to a meter. Now, with an actual neuron, the output would be here, but it would typically go to some sort of a nonlinear element that's sometimes called an activation function. And this element could be a sharp quantizer, like we did way back then. Now more favorable is a sigmoid. So the limit up above is +1, and the limit down below is -1. So the output could be +1 or -1 or anything in between. So that would be a complete model. And what inspired us to do things like this is that we're attempting to model the ideas that are accepted, the biological model of a living neuron, an animal's neuron, human or animal. So this is, the structure is Adeline, and the actual equipment that I'll demonstrate has a meter like that. So you'll be able to see what the output is for the given input. And you can see what the inputs are based on a pattern of lights. So you'll be able to see the whole thing. Now, to get to the training algorithm, we need to do a little bit of algebra. So we look at the output y, that's an analog output. The output y is equal to the vector x transpose times the vector w, and the vector w corresponds to the set of weights. So we're taking x1 multiplied by w1, x2, w2, xn, wn, and x sub 0 is +1 permanently. We go through the bias weight W0. So the x vector includes the +1, and the weight vector includes W0 together with all the others. So this is the output y is equal to x transpose W, and another way you can write it is W transpose x. The error. Let's say you apply an input pattern, an input vector. The error will be the difference between the desired response for that pattern and the output response for that pattern. So that difference is the error. You can see that here. The error is the difference between the desired response and the analog output. So the desired response minus y, and y is equal to x transpose W. And another way you can write that is W transpose x. They're both the same, because this product is a scalar, like that. The error is a scalar. Y is a scalar. X is a vector. W is a vector. Now, we're interested in minimizing the mean square of the error over the set of training patterns. So to find out about mean square error, we take the error and we square it. So we have a binomial, so we get the square of a binomial. So the square of the error is the square of d minus twice the product minus 2d x transpose W plus the square of this term. And the way I wrote it was W transpose x multiplied by x transpose W. And there are many ways you can write that, but if you do it this way, there's something interesting that develops. So now we're interested in the mean square error. So the MSE is equal to, and I represent that by the Greek symbol xi, and that is the expected value of the square of the error, and we're taking the expected value of both sides of this equation. The expected value of the square of the error equals the expected value of the desired response square minus twice epsilon the expected value of d x transpose. I should have said that while we look at the mean square error, we keep the weights fixed. So let's say we fix the weights, we apply in sequence all the input patterns one after the other, each input vector pattern and the associated desired response. And in each case, for each input vector, we look at the error, we take the square of the error, and then we take the average of the square of the error over the set of training patterns. That's what this is. So now we have the expected value of all those desired responses square. So it's the mean square of the set of desired responses minus 2 expected value of d x transpose. I pulled the W outside because we're going to keep the weights fixed. We're not going to adapt the weights. We're just going to apply the input patterns to see what the mean square error is. So we get the expected value of d x transpose W, and again W is fixed. And we take expectation over the variables, which are the input pattern vectors. So it's x transpose. All right, now the next line, xi is equal to the expected value of the desired response square minus 2 expected value of that. And I'm going to represent that expectation by p. And I'm going to represent this expectation by r. So that becomes minus 2, and this will be p transpose, as you'll see in a moment, multiplied by w plus w transpose r w. Now, we made a definition. I simplified this expectation. We made a definition that the expected value of dx we represent by the vector p. P is a cross-correlation vector. It's a set of cross-correlations between the desired response and each of the components of the input. So the input is a vector, the desired response is a scalar, the product is a vector, so the expected value of a vector is a vector, that's the p vector. So p is that, and this is p transpose w. In other words, you got expected value of dx transpose. So dx is defined as p, so that this becomes p transposed times w, plus this, we define r. R is a square matrix, is defined as the expected value of the input x multiplied by the transpose of the input x. The product of the two is a square matrix. You take the expected value of that, that's a square matrix. That's what R is. R is called the input autocorrelation matrix. It's the elements of the main diagonal are the mean square values of all the individual inputs. The off-diagonal values of this matrix are cross correlations between the various inputs to the Adeline. So that's what R is, that's what P is. And now we look at this, and what we see is that the mean square error is a quadratic function of the weights. So we'll say this is quadratic function of W. All right, so now for a given set of weights, apply all the input patterns and sense what the mean square error is. Now you can change the weights and run all the input patterns through it again and see what the new mean square error is because you've changed the weights. Do it again and again and again. So you realize that the mean square error as a function of the weights is quadratic, and you can represent it as a paraboloid. We can only draw it with two weights, so I did it for W1, W2, and drew a sketch of what the quadratic surface would look like. So the mean square error as a function of the weights is a paraboloid if I have only two weights. If I have many weights, we need more dimensions on the space. Instead of this being a paraboloid, it becomes a hyperparaboloid. Now we can look at this sketch and say what we want is to get down to the bottom of the bowl, this quadratic bowl where the mean square error is minimum. So we start out with an initial condition, sort of an initial guess. Set the weights to some initial value. Often they're just set to 0. And now you follow the negative of the gradient and go down to the bottom of the bowl here where the mean square error is minimum. At the bottom of the bowl, the set of weights that take you to the bottom of the bowl would be a vector. In this case, we call that vector W star. And another way we call it is a Wiener solution because it's the best linear least squares solution. Solution defining the minimum mean square error, or the setting of the weights, the setting of all the coefficients or the setting of all the synapses that minimize the mean square error over the set of training patterns. So we follow the gradient down to the bottom of the bowl, and that leads us, when we get there, what we have is an adjustment of the weights that we call W star, the best W, and that's the Wiener solution. Okay, so we're going to use the method of steepest descent. We come over here, and now we have an adaptive algorithm. So we're going to use steepest descent to get to the bottom of the bowl, to optimize the settings of the synapses. So the ideal steepest descent says the next set of weights, next weight vector equals the present weight vector plus a parameter mu that you choose, multiplied by the negative gradient. Now the bigger you choose mu, the bigger jump you make in proportion to the negative of the gradient. You need to go, mu should be a positive coefficient. You want to go in the direction of the negative gradient because that takes you down. If you went in the direction of the positive gradient, that would take you up, and every time you iterate, the mean square error would get higher and higher and the thing would blow up. So mu needs to be greater than 0, but it needs to be less than something. And that if you go beyond that, you'll take a jump that'll be so big, you'll go from one side of the bowl to the other and you'll be higher than you were in the first place. So every time you adapt, you go higher and higher, and again, it'll blow up. So mu has to be confined to be greater than 0 and less than some positive constant. But you, as an algorithm designer, get to choose mu, which controls the speed of convergence. This is just plain steepest descent. Now, this requires that you have the gradient. So in order to get the gradient, you'd have to measure it, and you'd have to take measurements of that surface. And that surface is based on data, and any measurement that you make, unless you make an infinite number of measurements of the gradient, you're not going to get an exact measure of gradient. So typically, you're going to be dealing with a gradient estimate based on a finite amount of data. So this is ideal. A practical steepest descent says next weight vector equals the present weight vector plus the change, and the change is mu times the negative of the gradient estimate. So estimate, we put a hat on top of gradient, the symbol for gradient. We put a hat on there, and that's now we can deal with gradient estimate. That's what we deal with physically, because that's all we're ever going to have in practice. Now, the definition of the gradient is the partial derivative of the mean square error with respect to the weights. That is to say, it's a column vector. The gradient is a vector. It's a column vector, which what you're dealing with is the partial derivative of xi with respect to w0, that's the first weight, partial derivative of xi with respect to the second weight, w1, partial derivative of xi with respect to the nth weight. So it's the derivative of the mean square error with respect to all the individual weights arranged in a column, and that's the definition of the gradient. Gradient estimate, we do something very strange. We take a single value of error from a single input pattern. We take the error and we square it, and we say that's the mean square error, and we know full well that can't possibly be true, because the mean square error has to be averaged over all the training patterns. But this is a gradient based on a single pattern, single training pattern, so it's the partial derivative of the error square with respect to the weight vector. So that derivative is what we call an instantaneous gradient. So it's not the true gradient, it's a gradient estimate based on a single sample of error, which is a very, very crude gradient. You never estimate a statistical parameter based on a single sample, but that's what we do here. So the derivative of the square of the error with respect to the weights. From elementary calculus, we know that the derivative of the square of something is twice something multiplied by the derivative of the first power of something. So this is equal to that by elementary calculus. So this, now the gradient hat, that's what this is 2 epsilon j. Now the derivative of the error with respect to the weights, we have to go back to our other blackboard frame and look at the error. And the derivative of the error with respect to the weights is just x itself, but you have a minus sign. So that derivative turns out to be minus x. So we put here for the derivative of the error with respect to the weights, minus x. So that's our gradient estimate based on a single sample of error, instantaneous gradient. So we take that gradient estimate and we put it over here for here. In other words, minus the gradient estimate comes out to be 2 epsilon xj. And now we can write this as wj plus 1 equals w, whoops, what did I do here? Wj plus 2 mu epsilon j xj. And the error epsilon j, instantaneous error, is the difference between the jth desired response for the jth input pattern. It's the difference between the desired response and the actual response, which is x sub j transpose w. This should really be w sub j. So now what we have is the so-called LMS algorithm, least mean square algorithm. That's a name that was given to it in the early 1960s by one of my doctoral students. Can't remember which one, but I certainly remember LMS algorithm, least mean square. So the pieces of equipment that I showed you before are an implementation of this. So I'll show you how these neurons operate. I'll train them for you, and then you can see how the whole process works. So I hope that all this algebra didn't create too much mystery. It's all quite simple once you get used to it. But unless you see the algebra, you'd never believe that these algorithms could actually work. Funny thing is, they do. The LMS algorithm is used in adaptive filters. These are digital filters that are trainable. And I should tell you that every modem in the world uses some form of the LMS algorithm. So this is the most widely used adaptive algorithm on the planet. And this algorithm was discovered by myself and Ted Hoff. This is 1959. And it's called Woodrow Hoff. It was discovered on a Friday afternoon in the autumn of 1959. I don't know the exact date. I wish I did. But I know it was in the fall quarter at Stanford, the autumn quarter, when I first met Ted Hoff. He was my first doctoral student. And we were arguing. I was explaining to him how adaptive algorithms work, and somehow, in explaining it, this thing came out between the discussion of the two of us. And so I wrote it on the blackboard. Across the hall from my office was an analog computer, and people today don't know what this is. But anyhow, it enabled us, within a few moments, Ted was able to program this on the analog computer. And we had this working. We had an Adeline working on an analog computer about a half hour after I wrote those equations on the blackboard. So then what we did, we decided that we can't use this analog computer all the time because it was somebody else's computer, and it took up a huge room. So we decided that we're going to build it on a chassis, aluminum chassis, and get potentiometers for the weights. We decided to make it easy to operate the algorithm, to use instead of smooth potentiometers as you'd like, we used potentiometers that were actually rotary selector switches, so they go click, click, click. So that's what we did. And we built this over the weekend. I know it was Friday because the next day the electronics stockroom was closed. We couldn't get any parts, so we had to go downtown in Palo Alto to an electronics shop and buy all the parts. And over the weekend, Saturday and Sunday, the two of us put all this together. And by Monday morning, I had this sitting in my office, able to demonstrate an algorithm that was to be called LMS, and demonstrate that this is a single neuron that is trainable. I'd like to make a few more comments about LMS algorithm. If you look at it, the next weight vector equals the present weight vector plus 2 mu epsilon x. What that tells you is that when epsilon, the error, is positive, you take the input pattern, multiply by 2 mu. Remember that mu is a positive constant. So 2 mu, you multiply that by x. So you're going to add this to the present weight vector to get the next weight vector. So the change is this. When the error is positive, you add the pattern, you add the x vector to the w vector to get the next w vector. When the error is negative, you subtract the x vector from the present weight vector to get the next weight vector. But the objective of all this is to make the error small. And the error is the difference between the desired response, in other words, what you want and what you've got. The error is the difference between what you have and what you want. So the error is going to be sometimes positive, sometimes negative. When it's positive, you add the x vector to the w vector to get the next w vector. When the error is negative, you subtract the x vector from the w vector to get the next w vector. Now I'll demonstrate that with a simple machine, an implementation of the ADALINE neuron. Let's take a look.